So we deal with sensible heat. Now remember, this is heat energy, the amount of heat a body can contain, or the amount of heat contained in the body. Now, the amount of sensible heat a body can contain is directly proportional to the change in temperature. So because the amount of sensible heat Q that the body can contain is directly proportional to the change in temperature, delta T. So when, mathematically, because Q is proportional to delta T, when we remove the proportionality sign, we introduce a constant and an equals so that we can get an equation. So that Q becomes equal to C delta T, where C is the constant. And the constant C stands for heat capacity of the body, heat capacity of the material. So, what is heat capacity? When we make the constant C the subject, then we can get the definition for heat capacity as C is equal to Q delta T. Remember, in physics, you can define a term, a quantity, using a formula that is related to that quantity. That is one of the techniques that we use to define quantities in physics. So you can define heat capacity as C equals Q delta theta. But remember that when you define it like that, you have to define the terms. For instance, if I'm defining heat capacity as C equals Q delta T, then I will go ahead and say that where C is the heat capacity, Q is the quantity of heat absorbed or lost from the body. In other words, quantity of heat contained in the body, and delta T is the change in temperature of the body. So, or you can also define it in words as this: the quantity of heat energy needed to change the temperature of a body by 1 degree Celsius or 1 Kelvin. Why are we saying 1 degree Celsius or 1 Kelvin? Change in temperature is the same. It doesn't matter whether it's in degrees Celsius or it's in Kelvin. So you can either define it using Kelvin or define it using degrees Celsius. It is, this definition in words is obtained from the definition in formula. That is the reason why you can write the formula as the definition for heat capacity, which is C. The heat capacity is a constant which is associated with the body that is absorbing the heat or losing the heat. Now the unit for heat capacity from the formula, you can see quantity of heat is in joules, change in temperature either degrees per degree Celsius or per Kelvin. So the unit can either be this or this. Why is this important? Sometimes WAEC, they can just ask you to write the unit for heat capacity. So it's important that you know what it is. Then the heat capacity C, the constant heat capacity C, experimentally is also found to be proportional to the mass of the body. The heat capacity C is also found to be proportional to the mass of the body. So what that means is that mathematically, the C, which is proportional to the mass of the body, when we remove the proportionality sign, we introduce another constant. Unfortunately, we use the same constant C, and this, if I had my own way, I would have changed them to different terms, but these are conventional symbols. We use capital C for the heat capacity, and we use small c for specific heat capacity. Small c is the specific heat capacity of the material. I will explain the difference between the two of them, heat capacity and specific heat capacity. For instance, I want to measure the amount of heat the sea can contain. The sea is a huge body, and to be able to measure the amount of heat the whole sea can contain to be a little bit difficult. So actually, to measure that amount of heat, I'm supposed to use Q is equal to C delta T, where C is the heat capacity. So what scientists do is that we pick a small portion of that, heat of that body. For instance, we take a sample of the sea, that is some mass of the sea, and then we determine the amount of heat that mass of the sea can contain. So this amount of heat that small mass of the sea can contain must in calculating that, we must use a constant which is related to that mass. That constant related to that mass alone is the specific heat capacity. So after that, we can then generalize it to the heat capacity. Or when we multiply the mass by the heat capacity, by the specific heat capacity, sorry, the small c, that will give us the heat capacity or the amount of heat that the body can contain. Good. So when we put this formula, capital C is equal to small c times m, into the previous equation, the equation 1, we get another relation for the quantity of heat a body can absorb or a body can lose. Q equals mc delta theta. Remember, the two formulas can be used at any point in time, provided that you have enough information for them. For instance, when you are given a question to answer and the question gives you the heat capacity, then you use the previous equation, equation 1. But when the question gives you the specific heat capacity, then you use this formula. Good. So the specific heat capacity of a body can also be defined, like previously we discussed, can also be defined by making C the subject in equation 2. So that we get C equals Q over M delta T. Or we can also define it in words as the quantity of heat energy needed to change the temperature of 1 kilogram mass of a body by 1 degree Celsius or 1 Kelvin. By 1 degree Celsius or 1 Kelvin. The unit for specific heat capacity from this relation, the unit for specific capacity is joule, that is Q, quantity of heat, per degree Celsius, change in temperature, per Kelvin, mass. And it can also be expressed in terms of Kelvin, like this one. Okay, now the Q, the quantity of heat, the amount of heat a body can absorb, the amount of heat a body contains, the amount of heat a body can lose. The Q is defined as, or the quantity of heat, which is the Q, is defined as the amount of heat energy contained in a body. It can also be defined as the amount of heat energy a body can lose, or the amount of heat energy a body can absorb. Now, in summary, the formulas for sensible heat can be put like this. We have already seen equation 1, Q equals C delta T, which is in terms of the heat capacity. Then in terms of the specific heat capacity, where we use the mass, Q equals mc delta T. Now, we know from our previous lessons that energy is neither created nor destroyed. This is the law of conservation of energy. So for instance, if I position an object at a height, at that height the object has potential energy. So when I release the object hit the ground. Let's assume that no other energy is formed apart from heat. When the object hit the ground, of course, there will be sound and other forms of energy. And we assume that all the potential energy at the point of release is converted to heat. In that case, we get the equation 3. That will give us Q equals mc delta T. mgh, where m is the mass, g is the acceleration due to gravity, and h is the height from where the object was released. Now, in terms of electrical energy, we use kettles, we use rice cookers, we use electric irons in our homes. So in terms of electrical energy producing heat, the Q becomes equal to, which is still sensible heat, the Q becomes equal to VIT, where V is the voltage, I is the current, and T is the time taken. And in terms of power, the Q is also expressed as power times time. So in summary, these are the formulas that you need to keep in your head. That questions can be asked you under sensible heat, and then you'll be required to make use of these formulas. Good. So factors that affect the quantity of heat absorbed or lost, or the quantity of heat contained in the body, that is the Q. Factors that affect the quantity of heat. We have temperature. Somebody may ask, why not change in temperature, but temperature? We use the change in temperature to calculate the quantity of heat the body can absorb or lose at that time. But remember, before the body was absorbing heat, it already had some heat inside it. So when we are talking about factors that affect the amount of heat the body can contain, we take into consideration the heat that was already contained in the body, hence the temperature of the body, the whole entire temperature of the body, not just the change in temperature. That is the reason why we use temperature but not change in temperature. Remember, if you write change in temperature, why could mark it down? Good. Then we have size or mass of the body. We have specific heat capacity or heat capacity of the body. All these are part of the equations. And then the nature of the surface, the nature of surface of the body. What do you mean by nature? The nature can be either the surface is rough or smooth. Remember, rough surface absorb heat easily or absorb heat faster or absorb more amount of heat. Smooth surface do not absorb large amount of heat. In the same vein, white surfaces do not absorb large amount of heat or do not absorb heat faster, but dull surfaces or dark surfaces absorb heat. So these are the factors that affect the quantity of heat absorbed or lost from the body. Now, so with this small sensible heat that we have discussed, let us look at this example. So we have this example to deal with. I'm going to do this one, I'll do the next one, then I'll give you the next one. I will give the next one to you to go and do at home, which you will send to me. Now, so we have this question. How much heat is given out when a piece of iron metal of mass 80 grams and specific heat capacity 46? This is supposed to, it's a typographical error. This is supposed to be 460. This is supposed to be 460. So because you have been given specific capacity, the unit, you see that because of the typographical error, there's a problem with the unit too. Good. So don't worry, they will see it. There's a problem with the unit too. You know the unit already, so let us go, we don't have time. So this is supposed to be 460 joule per kilogram per Kelvin. Cools from 100 degrees Celsius to 40 degrees Celsius. Let's forget about the unit. The most important thing is the values that we are dealing with. How do we solve this? Solution. Now, we quote our formula, Q equals MC delta theta, because we have been given the specific heat capacity. So we have to use the specific heat capacity formula. Then we do our substitutions. But remember, because the specific heat capacity is given to us in kilograms, the unit for the specific capacity is in kilograms. We cannot use the mass in grams, so we convert the mass to kilograms. So when we divide 80 grams by 1000, that will give us 0.008. Look at this. I told you that the value for the G is 0. You see that it is here. So if that's a typographical error, you understand? It's 0. Good. So the mass times the specific capacity times the change in temperature. 60. Where did we get this 60 from? 100 minus 40. Remember, change in temperature, we subtract the smaller temperature from the bigger temperature. So when we subtract 40 from 100, that will give us 60 degrees Celsius. And since change in temperature is the same, there's no need for us to convert this one to Kelvin before. We just subtract it and go your way. So finally, the amount of heat the body absorbs, the iron metal absorbs, when it cools from 100, when it cools from 100 degrees Celsius to 40 degrees Celsius, is 2,208 joules. Now, next example. The quantity of heat, 7,500 joules, is required to heat brass initially at temperature 26 degrees Celsius to a temperature T. If the mass of the brass is 200 grams and the specific capacity of the brass is 830 joule per kilogram per Kelvin, calculate the temperature T. In this case, the total quantity of heat has been given to us. Now, you as student, when you are solving the question, write the information, the parameters given to you in the question answer. It will guide you to not to pick wrong information for a correct parameter. If you don't write it down, you may make a mistake, but that one will not be marked. If you feel that you make a mistake, fine, you can go ahead and do it as I did it. So how do we solve this question? The same way, we use the same formula, Q equals MC delta theta. This time around, we are looking for temperature T. So we put in the values, we make T the subject, and finally we get 71.18 degrees Celsius. When you take your time and go through this one, you'll be able to solve it. Now, I want you to do this assignment for me. Now, after you have done this assignment, go to this website, log into the website, you will see your particulars there and post your answer on this website. I will pick it and mark it, and then we will interact. Thank you very much. Now let's go to determination of specific heat capacity of a liquid. Now we know heat capacity. We want to look at how to determine the specific heat capacity of a substance. How to determine the specific heat capacity of a liquid. Remember, we are determining the specific heat capacity of a liquid using method of mixtures. There are so many methods that we use to determine the specific capacity of a liquid. So many of them, which we will look at in our next lesson. But this particular one, we are dealing with determination of the specific capacity of a liquid using method of mixtures. How do we do this? In exam, if they ask you to do this, remember you are supposed to write the methods. But the methods won't appear here, but I'm going to describe how the experiment is to be done. So to do this, what we do is that we set up this apparatus. Now this is a stand that contains a beaker which contains water. So what we do is that we are dealing with the specific heat capacity of a substance, of a liquid, using method of mixtures. What are the mixtures? The name method of mixture stands for the three components. The water, the calorimeter that we'll be using to measure the heat. Remember, I have told you, the instrument used to measure quality of heat is calorimeter. So the water, the calorimeter, and the liquid, we are determining its specific heat capacity. Of course, it can be water. So the liquid, the calorimeter, and a metal whose specific heat capacity is known. That is very important. You pick a metal whose specific heat capacity is known. So what we do is that we set up this, then we put our thermometer in, and then what we do is that we get an electronic balance or any balance that we use to determine the mass of the substance that we want to measure, that we are going to use, the mass of the metal that we are going to use for the experiment. We determine the mass of the metal. Then we record the mass of the metal as mm, which stands for the mass of the metal. Now, what then do we do? We have recorded the mass of the metal. We put it down. Then what we do is that we then transfer the metal into the container. Then we set fire under the container so that the metal then begins to heat with the water inside the beaker. The function of the thermometer here is to record the temperature, the final temperature of the metal which is inside the beaker. What then do we do? We pick our calorimeter. So we put the calorimeter on a balance, then we determine the mass of the calorimeter with this stirrer. That is very important because the stirrer is also going to absorb heat. So we put the stirrer in the calorimeter, and then we determine the mass of the empty calorimeter, the mass of the empty calorimeter with this stirrer. Then we put it down as, and that is MC, mass of the empty calorimeter, MC. Then what we do is that we fill the calorimeter up to 2/3 of it with the liquid that we are going to determine the specific capacity. Then what do? We then measure the mass of the liquid and the calorimeter again. Why are we trying to do this? We want to determine the mass of the liquid only. And liquid has to be in the container. So we have already determined the mass of the calorimeter only. So when we pour the liquid into the calorimeter, we then determine the mass of the liquid by subtracting the mass of the calorimeter only from the mass of the liquid and the calorimeter. That will give us the mass of the liquid, that is ml. These parameters are very important because these are what we are going to use to form our equation. Then the next thing we do is that we then put our thermometer, another thermometer, into the the calorimeter, and then we measure the initial temperature of the water and the calorimeter. So that initial temperature is recorded as θ1, the initial temperature of the water and the calorimeter. So to do this, you have to wait small for the temperature of the calorimeter and that of the liquid become equal before you take that measurement. So after you have poured the liquid in, you wait small for some time, and then you put your thermometer in, you determine the initial temperature of the water and the calorimeter. Then after we have done that, what we do is that we transfer the mass quickly into the calorimeter from the mass that we have heated. Remember, before we transfer it, we determine the reading of the thermometer here. The reading of the thermometer is the temperature of the metal and the water inside this one. This thermometer will record the temperature of the metal when it's inside this one. So we record that temperature as the initial temperature of the solid inside the boiling water before we do the transfer. Now, there are certain things, certain precautions you need to take when you're doing this experiment. One of them is this. When you are transferring the metal into the calorimeter, you do it as quick as possible. Why is that important? You know, sometimes in practicals, students want to cheat the system small. So what we do is that we set up the heating source for the students, all the students at one point, so they will come and heat their metal and go. So once the student has removed the metal from the container, he wants to use that opportunity to cheat. So he's holding the metal in air whilst asking his friend, what did you get for the question 2? Forgetting that the metal is losing heat to the surrounding. That is the reason why you are supposed to transfer the metal quickly from the heating source to the calorimeter to prevent heat loss to the surrounding. That is one precaution. Precaution number 2. When you transfer the metal, don't drop it into the calorimeter. What you need to do is that you bring the metal and lower it gently into the calorimeter. Why? If you drop it into the calorimeter, there's a possibility that some of the liquid inside will be splashed off. Remember, you have already determined the mass of the liquid. The mass of the liquid as ml. So if some mass of the liquid is splashed off, you are going to encounter error. That is the reason why you drop it gently. Precaution number 2. So as we proceed, some other precautions will come. Then what we do is that we stir. So you hold the stirrer and then you stir the water to make sure there is uniform distribution of the temperature. That is also another precaution that you are supposed to take. You stir the liquid to make sure there is uniform distribution of temperature. So when this happens, the mercury level will then begin to fall. So the mercury level will rise. Why? Because the temperature of the metal was bigger. The θ2 was bigger when it was here. So when you bring it into the calorimeter, the temperature of the calorimeter and the water are small. That is the θ1. So because of that, there is going to be exchange of heat. So whilst the metal is losing heat, the calorimeter will be gaining, the calorimeter and the water will be gaining the heat until the 3 of them will reach thermal equilibrium. Method of Mistius, the 3 of them reach thermal equilibrium. At that point, the temperature of the metal is equal to the temperature of the calorimeter and the water. Good. So you continue to stir until that point is reached. Then you determine the final temperature of the mixture, which is the 3 of them. Then, because we are dealing with specific heat capacity, now what we do is that we are dealing with quantity of heat. We need a specific heat capacity of the 3 components too. So we write them down. Then the theory of the experiment, the most important, the theory of the experiment. The theory behind this experiment is that while the metal is losing heat, the water and the calorimeter are getting it. So we say heat loss by metal is equal to, continue, heat loss by metal is equal to
heat gain by,
thank you, heat gain by water and calorimeter. Excellent. Heat gain by water and calorimeter. So we use this theory, heat loss by metal is equal to heat gain by water, liquid and calorimeter. So from that, we write it in terms of Q, then we put in the values. So mass of metal, specific capacity of metal times change in temperature. This is very important. The change in temperature. Remember, the initial temperature of the metal, which was θ2, is bigger than the final temperature of the metal, theta 3. Most students get confused here. They pick the 3 and the 2, and they always want to subtract theta 2 from theta 3 because they feel that the 3 is bigger than the 2. No. We subtract the smaller temperature from the bigger temperature. From the theory that we know, the final temperature, theta 3, is less than the initial temperature, theta 2 of the metal. So we subtract the smaller temperature from the bigger temperature. Mass of the liquid, specific capacity of the liquid, change in temperature, theta 3 minus theta 1. The final temperature of the mixture is theta 3. That is for the liquid and the calorimeter. The initial temperature is theta 1 for the liquid and the calorimeter. Good. So, and then the quantity of heat absorbed by the calorimeter, that is also captured as MC, CC, change in temperature, theta 3 minus theta 1. So from this, remember, our objective is to determine the specific heat capacity of the liquid. So we make Cl the subject. When we make Cl the subject, we get the specific heat capacity of the liquid. So thank you very much for today's lesson. We shall meet again and continue with latent heat. Okay, before we go to latent heat, we have to deal with some other types. So what I want you to do is that follow me on BJ Online. That's my YouTube channel, BJ Online, for some of these videos, and then